Welcome to an exciting new topic, motion in a plane. Up until now, we've mainly looked at motion along a straight line, one-dimensional motion. But most objects in the real world don't just move back and forth. They move around in space, often in two dimensions. This motion in a plane involves both a horizontal direction, which we call the x-axis, and a vertical direction, the y-axis. To thoroughly describe such motion, we use vectors. Vectors are special quantities that tell us not only how large something is, but also which way it points. Position, displacement, velocity, and acceleration in two dimensions are all described by vectors. This comprehensive approach lets us understand where a particle is at any moment, how it moves, and how its motion changes. By bringing in components along the x and y directions, we extend the ideas we learned for one-dimensional motion. This skill is essential for later topics, such as projectile or circular motion, where motion's direction changes continuously. Today, we begin by understanding how to represent the position of a particle in the plane using the position vector. This is foundational, so pay close attention. Next, we'll see how displacement and velocity relate to this position vector. Let's get started. Let's understand how to specify where a particle is in a two-dimensional plane in figure 3.12. Imagine we have an xy coordinate system, two perpendicular lines crossing at a point called the origin. Now, suppose a particle is located somewhere in this plane at point P, which is a certain distance rightward along the x-axis and upward along the y-axis. To represent P's exact location, we use the position vector, denoted as r. This vector starts at the origin and points directly to P. It is written mathematically as r equals xi plus yj, where x and y are the particle's coordinates along the x and y axes, respectively. The symbols E and J are unit vectors that point along the x and y axes, indicating direction. Think of these unit vectors as arrows of length, one pointing along each axis. So E tells us how far to move along xi, and yj tells us how far along y. Together they combine to position vector r, an arrow from the origin straight to the particle. This vector completely locates the particle in space at that instant and sets the stage for analyzing how it moves. Next, we'll see how a particle's change in position is described using displacement vectors. Now that we've established how to locate a particle at a single instant with the position vector, let's move to understanding how its position changes a key part of motion. This change is represented by the displacement vector, denoted as delta r. Imagine the particle moves from one point P to another point P prime at a later time. Each of those points has a position vector, r prime minus r, respectively. The displacement vector is the difference between these two. Delta r equals r prime minus r. We can picture delta r as an arrow pointing from P straight to P prime. It does not depend on the path taken, only the initial and final positions. Breaking it into components, the change along the x-axis is delta x equals x prime minus x, and similarly for the y-axis, delta y equals y prime minus y. Thus, delta r equals I hat, delta x plus j hat delta y. This simplification allows us to handle motion along two perpendicular axes efficiently. Displacement is fundamental because it captures the net change in position, a vector quantity reflecting both how far and in what direction the particle has moved. Next, we will connect displacement to velocity. Let's connect displacement with velocity. Velocity tells us how fast and in what direction an object moves. But what's actually measured is often the average velocity over a period of time. Mathematically, average velocity v is the displacement vector divided by the time interval. V equals delta r divided by delta t. Because displacement itself is a vector, average velocity points in the same direction, telling us the overall direction of motion. When we substitute the displacement's component form, velocity becomes v equals I delta t over delta x plus j delta t over delta y. Here, delta x by delta t is the velocity along the x-axis, and delta y by delta t along the y-axis. This component-wise approach lets us analyze motion independently along two perpendicular directions. Average velocity bridges the gap between position and how motion progresses over time. Next, we will explore how velocity can be instantaneous and how calculus gives us a precise meaning of it. Average velocity is useful, but sometimes we want the velocity right at a precise instant. This is called instantaneous velocity. To find it, we imagine shrinking the time interval delta t between two positions closer and closer to zero. Mathematically, as delta t approaches zero, the average velocity vec v equals delta r divided by delta t approaches the instantaneous velocity. Formally, this is expressed as a limit. V equals limit delta t to 0 delta r delta t. In calculus terms, this limit results in the derivative of the position vector with respect to time. V equals dr by dt equals hat I dx by dt plus hat j dy by dt. This derivative defines how fast and in what direction the object is moving at any given moment. Importantly, the instantaneous velocity vector is always tangent to the particle's path at that instant, pointing in the direction of motion. That means for curved paths, the velocity vector changes direction continuously. Understanding this concept is key before we explore acceleration and forces affecting motion. Up next, we examine velocity components more closely. We know velocity is the time rate of change of position, but since motion is in two dimensions, it's useful to analyze velocity component-wise along each axis. The position vector depends on time. R of t equals x of t hat I plus y of t hat j. Differentiating each coordinate with respect to time yields the instantaneous velocity component. Vx equals dx over dt along x and Vy equals dy over dt along y. Thus, velocity vector is v equals Vx hat I plus Vy hat j. This means the object's overall velocity combines how fast it moves horizontally and vertically at that instant. Understanding these components lets us handle more complicated motions by focusing separately on each dimension. It's like figuring out how far you move forward and sideways at the same time. Next, we'll look at calculating the magnitude and direction of this velocity vector. Once velocity has components along x and y, we often want to know two things: how fast the object is moving overall, and in which direction it's headed. The overall speed, or magnitude of velocity, comes from the Pythagorean theorem, because Vx and Vy form perpendicular legs of a right triangle. The speed is v equals the square root of Vx squared plus Vy squared. For direction, we calculate the angle theta the velocity vector makes with the positive x-axis using theta equals tan power to negative 1 Vy by Vx. This inverse tangent gives the angle in degrees or radians, defining the direction precisely. Having both magnitude and angle tells us everything about velocity, which is crucial for predicting motion path, especially in two dimensions like a ball's flight or vehicle movement. For example, velocity components determine how a projectile moves horizontally and vertically simultaneously. Understanding these calculations lets you interpret vector quantities comprehensively. Next, let's apply these principles towards acceleration in two dimensions. After velocity comes acceleration, how velocity itself changes over time. Just as velocity is a vector, acceleration is also a vector, meaning it has magnitude and direction. Average acceleration is defined as the change in velocity divided by the elapsed time. A equals delta v divided by delta t. Because velocity has components along x and y, acceleration components similarly are ax equals delta vx over delta t and ay equals delta vy over delta t. These tell us how quickly velocity changes in each direction. Acceleration could mean the object is speeding up, slowing down, or altering its path direction, all captured by this vector quantity. We break acceleration down the same way as velocity, enabling simpler calculations and clear physical interpretation. Understanding acceleration in 2 dimensions sets the stage for analyzing forces and Newton's laws later on. Next, we will see instantaneous acceleration and how calculus refines this concept. We refine the concept of acceleration by considering the instantaneous acceleration, the exact acceleration at a moment, rather than over a finite interval. Mathematically, instantaneous acceleration vector A is defined as the limit of average acceleration as the time interval approaches 0. A equals limit delta t to 0 delta v slash delta t equals dv slash dt. Breaking this down into components, instantaneous acceleration has x and y parts that are derivatives of the velocity components with respect to time. A sub x equals dv sub x over dt. A sub y equals dv sub y over dt. This definition captures how velocity's magnitude or direction changes exactly at a point. Graphically, as we get closer to that instant on a path, average acceleration vectors from successive intervals approach the instantaneous acceleration, which may point differently due to motion curvature. Mastering this concept is crucial for analyzing forces and motion in physics. We will also explore common misconceptions to ensure clear understanding. Acceleration in 2 dimensions becomes especially interesting for objects moving along curved paths. The velocity vector v, representing instantaneous speed and direction, changes both magnitude and direction as the particle moves. The key to understanding acceleration is to look at how velocity changes between nearby points on the path. Figures 3.15a to d show this graphically. At each position along the curve, the velocity vectors have slightly different directions and lengths. The change in velocity between 2 points delta v equals v prime minus vi points in the direction of the acceleration vector. As the time intervals between these points get smaller, the average acceleration vector approaches the instantaneous acceleration. This acceleration vector often points toward the center of curvature, showing how the object turns while moving. These visualizations emphasize that acceleration results not only from changes in speed, but also from changes in direction, a vital concept for analyzing curved motion, such as in circles or waves. Our next slide analyzes velocity and acceleration components with an example problem. Before we conclude this session, let's clear up some common misconceptions students have about motion in a plane. First, many confuse displacement with distance traveled. Displacement is a vector showing shortest distance from start to end points, while distance is the total length of the path, always positive and scalar. Second, velocity and speed are often mixed up. Velocity includes direction and magnitude. Speed is just how fast something moves and is the magnitude of velocity. Third, people assume acceleration always points in the direction of velocity. However, acceleration can be perpendicular. This happens when direction changes, but speed doesn't, like in uniform circular motion. Another confusion is mixing average and instantaneous velocities. Average is over a finite time interval, whereas instantaneous velocity is at a precise moment found using limits. Understanding these distinctions sharpens your analysis of motion problems and improves conceptual clarity. Next, we will summarize key takeaways and apply these ideas in examples. Let's apply everything we've learned with an example. Consider a particle whose position vector changes with time, as r equals 3.0 t hat, I plus 2.0 t square hat, j plus 5.0 hat k. This means it moves along the x-axis at a rate proportional to time, along the y-axis at a rate proportional to the square of time, and stays constant along the z-axis. To find the velocity, we differentiate each component. Derivative of 3.0 t hat, I, with respect to time is 3.0 hat. I since derivative of t is 1. Derivative of t squared is 2t of 2.0 t square hat. J is 4.0 t hat j due to the power rule. Derivative of constant 5.0 hat k is 0. Thus, velocity vector is vt equals 3.0 hat I plus 4.0 t hat j. Next, acceleration is rate of change of velocity, so differentiate velocity components. Derivative of 3.0 hat I is 0. Derivative of 4.0. T hat j is 4.0 hat j. So acceleration is constant at equals 4.0 hat j meters per second squared, directed entirely along y-axis. At t equals 1.0 second, velocity vector is 3.0 hat I plus 4.0 hat j. Its magnitude, or speed, is calculated using Pythagoras as the square root of 3.0 square plus 4.0 square equals 5.0 meters per second. The direction angle theta with respect to the x-axis is tan to the power minus 1, 4/3 equals 53. This clearly shows how vectors, derivatives, and trigonometry combine to describe motion in the plane. Next, we'll summarize key ideas and prepare to extend these concepts. Let's wrap up what we've learned about motion in a plane. We use the position vector r equals x hat I plus y hat j to pinpoint locations in two-dimensional space. When a particle moves, its change in position is described by the displacement vector, delta r equals r. Prime minus r equals hat, I delta x plus hat, j delta y. Velocity is fundamentally the rate at which position changes. Taking the time derivative, v equals dr over dt equals vx hat, I plus vy hat j, where each component tells us how fast the particle moves along the x and y axes. Similarly, acceleration is the rate at which velocity itself changes. A equals dv over d, t equals ax hat I plus ay hat j. To fully describe the particle's motion, we calculate the magnitude of velocity using v equals the square root of vx squared plus vy squared, and its direction using theta equals the tangent to the power of -1 of vy divided by vx. These vector tools give us a complete, detailed description of motion in 2 dimensions. Mastery of these basics improves your understanding of physical phenomena and prepares you to analyze more complex motions. Having built a solid foundation in describing motion in a plane using vectors, we are now ready to explore applications like projectile and circular motion, where these ideas come alive in more dynamic ways. Understanding how to break down motion into components and analyze velocity and acceleration vectors prepares us to incorporate forces and Newton's laws in upcoming lessons. We will see how these vector quantities dictate the motion of objects thrown into the air, moving along curves, or affected by various forces. Developing fluency in vector analysis is essential for mastering physics and solving real-world problems accurately. Keep practicing these concepts by working through examples and visualizing motion intuitively. This will deepen your understanding and prepare you for more advanced topics. Next class, we'll build directly on these ideas to explore forces acting on particles in motion. Until then, keep thinking about how vectors help unravel the mysteries of motion in our world.